So we would like to see also a memory operand example. We have a C code, a higher level code that actually say that G is equal to H plus A of 8. A is an array and 8 is the 8th location. This is the higher level code. Our job actually is to go deep a little bit more, and we need to understand. We need to understand how we can implement this in details, and how the assembly language will handle something like that. But actually, the most important thing is how things are basically happened under this layer, under the layer of higher level language, because this is we are going a little bit more deep to interface with the CPU and to understand more about how we can actually interact with the CPU. And accordingly, we need to go a little bit further in understanding the steps to do such implementation. And because of that, we are giving you that this G is basically saved in a location inside the register called S1. This H is saved inside a location in my register that is called S2. And also the base address of A is in S3. So I have here a register. This register is basically 32 rows. And also the width of this is 32 bits. I'm telling you that this H is saved in one of the location. Okay, so this H in one of the register called S2. S1 has the G, and then S3 has the base address of A. What you need to do is take this, whatever is in base address of A, added to H, put the results in G. But as you can see from here, that H and G is just variable that is inside the register. The problem that I'm facing here, that is telling me the base address of A is in this location, but this is address, not the value that I need to add actually. So I have to think that I should go somewhere to bring this data from, and then add it to H, and then put the results into G. This is what I need to do, and this is what we need to understand now, how we can do that. So first of all, if I'm telling you like I'm saving the base address of A, so this means that basically I am pointing out to a certain address inside my memory. And I'm pointing out to a certain address inside my memory, but I'm giving you only the base address. And I'm telling you, please go to A of 8. That array that has like several values or several like saved values. There's A of 0, A of 1, A of 2, A of 3, and so on and so forth. I would like you to go to A of 8, bring or retrieve these values or read these values from the memory. But I'm not telling you where is A of 8, I'm telling you the base address. Before going in details, something like that, and to understand where I can go to the memory, let's cover an example from our life, and then we'll try to apply the same concept into the memory. Assuming that we have a street, and in this street, we have basically several houses. And this is first house, second house, third house, fourth house, and so on and so forth. And in that street, the first house has the number of 200, for instance. Let's say that this is the example. You have a street, a certain street. The first house address of that street is 200. The other information that I'm giving you, that we are counting by 4 in that particular street. Usually, of course, the case that we have a right hand side and left hand side. One of the hand side, I'm counting the even number. Another hand side, I'm counting the odd number. And then that's why I'm just counting by 2, correct, on each of the sides. This is what we usually have. But let's say that we have a new system that we are just counting by 4. For whatever reason, just like take it as a fact. So we are counting by 4. If I am counting by 4, I know that this next house, it will be 200 plus 4. So the address of this is 204. How about the following address? It is 200 plus 8. So it is 208, and so on. So what I'm actually doing is what? I am getting the base address, which is 200, plus 4, which what I'm counting by, multiplied by the house number, or where it is located inside that street. So let's say this is the 0 house, 1 house, second house, third house, and so on. So it will be 4 multiplied by 312. So it is 200 plus 12. So it is 212. If I'm asking you about the nth, it will be what? It will be, let's say, like this will be the base address plus counting value, which in my case is the 4, multiplied by the nth location of the house. Correct? And accordingly, I can give you the address, any address in that particular street, because I know what is the base, I know by how much I'm counting, and I know which house, or you will ask me which house you would like actually the address. It is the 5th, it is the 6th, it is the 7th, the 10th, and so on and so forth, and can easily calculate the address. So that means that I don't have to give you the address of each house. I can give you what is the first house address. I'm giving you like how counting by, like in this case is 4. And then you can calculate the addresses of all of the houses. Shouldn't be a problem at all. Is that right? But the same exact concept, we need to apply it, but in the case of the memory. How? Assume right now that I have a memory, and this memory has different locations, of course, which is different rows. And this width of the memory is 8 bits. And if it is 8 bits, so this means that I will need 4 different rows to save the word, because basically the word is equal to 32 bits. If I would like to save 32 divided by 8, it is 4. So 1, 2, 3, and then the 4th. The beginning base address is 0. Correct? And then second byte is 1, 2, 3, and then my second word begin at address 4, and then 4, 5, 6, 7, and then the next word will begin at 8, and so on and so forth. Here will be the 12th. So basically, this will be my first word. This will be my second word. This will be my third word, and so on and so forth. And again, I'm counting by 4. So in order to know any locations of this memory, I can give you where is the base address and how much I would like to go from that base address. And accordingly, you can calculate where is the address. It's exactly the same as the number of the house. I can give you the base address. and I would like how far is my house there, and by giving you by how much I'm counting, yes, then you can calculate the address of the house. Here is exactly the same concept. I am giving you that basically the A of 0 is saved inside my register at a certain location called S3, and this S3 is not but pointing out to one of these addresses, either or. I'm telling you that this is the base address. If the base address of here, so I will begin counting from here. If the base address of here, I will be counting from here. If the base address from here, I will be counting from here, and so on and so forth. So if I'm telling you that the base address of A of 0 is here, so that means that this actually is A of 0. Correct? And A of 8 is not but, again, the base address plus 4 multiplied by the house number, or in our case, the 8th location in my array, so multiplied by 8. So it will be equal to the base address plus 32. So no matter what the base address, I will take that base address and add 32. I will know what is the location of A of 8. So if my A of 0 is here, it will be 0 plus 32. So basically, whatever 32 is here, then this is my A of 8. If my A of 0 is here, then I will add 32 to 4, and then I will go to the address and then know that this is A of 8, and so on and so forth. The main thing that is always 32 rows away from my base address, given that this is 8 bits and my word is 32 bits. If this is the case, I'm counting by 4. Correct? What I'm telling you that, okay, as soon as you will arrive or you will know where is A of 8, please, I would like to add, you know that this is the address of A of 8. I would like to take this value, please add it to H and put the results in G. So this has to be added to a certain H here, and then put the results into G. But the problem, as we mentioned earlier, since we are in a RISC processor, we can't do the operation inside the memory. I have to do what? I have to copy these things inside my register to a certain place here. Let's say, like, I will call this T0. I will copy whatever I have here to T of 0. Then I have my T of 0. I will add it to H, put the results in G. So now we understand the concept, but then how I will be able to write the assembly, this is what we'll see now. So we arrived to the A of 8, and we know that this A of 8 is 32 location away from my base address, which is in S3, and this is how the assembly will write that. It is 32 location away from my base address, which is in S3. Please load the word. As soon as you will get the A of 8 from this place, load it or copy it or retrieve it or read it to a certain register inside my register. It's called T of 0. So now I have saved in a certain location here called T0. I saved A of 8. After I have A of 8, please add it to H, put the results in G. Please add whatever I have in T0 with whatever I have in H, and H is in S2. Please, after this addition, put the results in G. G is what? Is S1. So then I will do the S1. By adding these two codes in assembly, I have done exactly the same things that has been implemented or just mentioned in my higher level code. But I just like dig in a little bit in details to see how things are moving between the register and the memory in order to do that. But I would like to highlight an important thing, that now I told you that the example that we have only width of 8 bits. Assuming now that I have 16 bits width, by the way, by default, if nothing specified, then the width will be 8 bits. In the exam or in the quiz or in something, the width will be 8 bits. Assuming that it is 16 bits, and this is my memory. Of course, if I have a word that is equal to 32, then I have to save one word in only 2 rows instead of 4 rows. So basically, I'm counting by 2. So this will be the first word, 0 and 1, and then this will be 2. And then this will be my second word. And then I will have the other one begin at 4, which is basically the third word, and so on and so forth. But in this case, I'm counting by 2 instead. So we will apply the same exact rule. The only difference that now I will have the base address plus 2 instead of 4 multiplied by the ith location. It's exactly the same concept, but the only difference is how much I'm counting by. And this can differ from an assignment to assignment, or from a quiz to a quiz, from an exam, and so on and so forth. Conceptually, you need to apply the same things, but the number itself will be different. I can tell you also that the word is no longer 32. You have another example that the word is 64, and you still have a 16 bits. If you have a 16 bits and 64, then you actually need to write that in how many? 4 different rows, because 64 divided by 16 will give us 4 different locations, and this will be the first word, 0 counting by 4, and so on and so forth. If this is 32 and it's 64, then again I'm counting by 2, and so on and so forth. So I can change these numbers, but conceptually I have to do exactly the same thing. After I arrived to the correct location, after I have arrived to the correct location of A of 8, let's say that this is my location. Please, this is the address. I know the address now, but I don't know what is inside. I have to move it or copy it to a certain particular register here. Copy it here. Let's say that this is T of 0. Please add whatever you have in T of 0 to H, and then put the results in G. But then the next question is, how about if I would like actually to take this G to save it back to the memory? What I should do? I should actually move this to a memory, to a certain other location that you might specify in your program. And we will see an example in how to do that. But conceptually, we can do that. Here is another example that my higher level code, C code, is actually asking me to do the A of 12 is equal to H plus A of 8. So H plus A of 8 is exactly as we mentioned earlier. It's the same exact things. So I will go with the base address, which is written in S3. I will go 32 away from that particular base of address. I will get the A of 8. Please load word or load the A of 8 to a temporary register, let's say T0, and then I will add it to H. H is in S2, and then we'll put the results in a certain particular place inside my memory. Let's say I will put this in a temporary register T1, or I will override this T0, either or. But after I have this in the register, as I mentioned previously, after I have this in the register, how I can save it in A of 12? Interestingly, as we mentioned earlier, that if I have the memory here, I can go from the memory to the register by something called load word, meaning reading from the memory. And I can write to the memory by something called SW, store word. This is load word. So by doing that, after I have this in a certain particular place, let's say T1, what I need to do, please store word T1 to that particular location. And let's say that that particular location is called A of 12. My job is to know where is this A of 12 inside my memory. But we will apply the same exact concept, that where is the base address? And it will be 4 multiplied by the ith location from that particular base address. And since 4 multiplied by 12 is 48, so I will be basically 48 away from my base address instead of 32. So I will do the exact same things. This line and this line was from the previous example. I load the word A of 8, which was 32 away from my base address, load it to T0. Please, now it is here. Now it is here at a certain particular location, T0. Let's say here T0. Please add this to H, which is in S2. Add this to S, which is the S2, which is the H. And this put the results either in another register, or I will override the temporary register T0. It doesn't matter, because I will not use, I will no longer need the actually T0. I have already copied the A of 8, and that's all. I can overwrite it. It's not a big deal here. And I can override this T0, T register. What I need to do is, after I have this value, which say like here, which is here as an example, I have to store word this in A of 12. How I can find A of 12? Store word the T0 to a place, to a house that is 48 addresses away from my base address 30 SS3. And by this, so what I need to do in this case, assuming that this is, for instance, my T of 0, what I need to do is whatever I go to the A of 12 and save it here, and this will be my base address plus 48, because I do 4 multiplied by 12. So this will be 48 away from my base address, assuming that my base address is address 0, or at A of 0 is here, if this was the case. So let's, see this, how is the implementation of something like that, just by the animation supported by the text book. So here again, I have the G at a certain location. I have the H at a certain location. And I know that the A here at a certain location, and this is the base address. The base address of A is 5,000. So I know that the base address that is saved in S3, as we mentioned earlier, had the value of 5,000. 5,000, as you have seen, it wasn't mentioned anywhere, because I don't care about that. I just need to care about where it is located. And as soon as I will go to S3, my hardware will read that. We'll cover this in details later on, but for now, it doesn't matter actually if it is 5,000 or 6,000 or 7,000. I will just read that number, and then I will go to that location inside my memory. As soon as I know that this is 5,000, so basically my base address of A is 5,000. And in this example, assuming that my memory width actually is 32, and that's why I'm counting by 1, as you can see from here, because the whole word is saved in one row, and that's why I'm counting by 1. The first word here, second word in second row, third in the third row, and so on. I don't have to write this in 4 rows, as we mentioned earlier. This is just 1 row. Okay, and then I know that now A of 8 is basically, since 1 row means 1 word, so it will be 8 rows away. So the address of that will be 5,008. What I need to do is what? Take that, the value that is inside that 5,008, copy it to a certain register here, and then add it to H, put the results in G, as we will see now. So let's say 25 is here. Of course, this 25 will be moved to T0, and then now I have to add whatever in T0 with 35 is equal to 60. Because whatever I have in 25 plus H, put the results in J is 60. If I would like you to move this 60 to a certain other location here, I would say like this is maybe A of 4, and then you will know that this 60 has to move to an A of 4th, which should be in 5004 in this example. So you have to do store word from S1 all the way till 4 S3. We'll see this in the other example, something like that. Just to mention, most important things to mention here that differ from whatever I mentioned, that here the memory width is 32. Here is another example, but this example is taking the same scenario that we mentioned, that the width is only 8 bits. And since the width is 8 bits, as you can see from here, I'm counting by 4. 5000, 5004, 5008, and so on and so forth. Again, the same thing. We'll do exactly this by the plus this as we did earlier. So here is the base address of A, which is written here. This is A of 8. This is A of 8, of course, at 32 blocks away from the base address. We need to add this value to H, of course. And put that in a certain value there and know that A of 12 is copied to A of 12. But before that, we need to know where is A of 12. Of course, A of 12 is not but 12 multiplied by 4 because I'm counting by 4. And this is the 12th house. So 12 multiplied by 4 is 48. So I know that it is an address 5048. Why is this useful? Because this is what I will use to save all of the results that I had at the very end to this location. So now I'm adding this by this, it is 60. I'm overwriting the T0. Then this 60, I have actually to move it here in A of 12. Because at the end, I need to put that in a certain particular place. I might save that place inside my register, or I might use that inside my address. Couple of things to highlight also for the differences between registers and memory, that registers, of course, are faster to access than the memory. We will deal with the memory only when we do a load or store. This will be the only place inside my code that I will deal with the memory. If I have any other things, I mean, this won't be like dealing with the memory in that case. Also, compiler must use registers for variables as much as possible. And basically, the reason behind that, as we explained, that I would like to access things that is much faster than the others. I mean, and because the memory is a little bit further away from the CPU and the access time is higher, extremely higher comparable to the register. So that's why I would prefer that actually all my variables will be inside the register, but which is not always the case. But as much as I can, I should save all the registers, all the variables in the register. And that's why, of course, only spill to memory for less frequently used variables, since each time I would like to access a variable inside my memory, I'm losing time. And if I'm losing time, then the whole throughput of the operations will be, of course, less. It will decrease. Another important things we would like to highlight, which is an immediate operand. Let's say that I have a constant that I would like to add to a register or a certain particular registers, let's say S3, and then put the results in a certain particular registers inside one of the rows inside my registers. But in earlier, what we have done, that add this to this, put the results in this. and then I just do the add operation. The issue appears when I have a constant. So instead of a register here, I have a certain constant which is called 4, for example. In this case, I can't use the addition, just the add. I have to use add immediate, add I. So add I, will understand later on in details how this is different than just the add, but this is just like take it for now. Interestingly, the MIPS does not support a subtract immediate instruction by default. In this case, we just use a negative constants, meaning that if I would like to do a subtraction S1 minus 1, then I will S1, whatever is there, minus 1. So I will do addition between S1 and minus 1, which is gives me exactly the same results. Of course, these small constants are something that is common, and with this immediate operand will avoid a lot of instructions, as we will explain later on. Another important things in MIPS is the constant 0. So inside my register, interestingly, the first register is called the 0 register, and it holds actually the value of 0 and cannot be overwritten. I can't change it. The first one is a 0 register, and you can easily use it whenever you need. And it can't be overwritten, just reserve it for 0. One of the common usability of that, when I would like, as an example, to copy certain place, let's say like I have S1 register to another place, let's say T2 register. If I would like to copy this here, I will not do anything but add S1 to 0, put the results here. Add S1 to 0, put the results in T2. So this means that I have copied whatever I have in S1 to T2. Would like also to remind you about the unsigned binary integers, that actually it can go from the range from 0 all the way to 2 to the power of n minus 1. So let's say you have 3 bits. If you have 3 bits, so you can count from 0 all the way to 2 to the power of 3 minus 1. Basically, you can go all the way till 1, 1, 1. And 1, 1, 1 is basically 7. So you can go from 0 all the way to till 7, as you can see from here. 2 to the power of 3 is 8, minus 1 is equal to 7. So you can go from 0 to 7. You can apply that even if you have like 32 bits. It is 0 to all the way to 2 to the power of 32 minus 1, which is 4 gig, as we have explained earlier. Also, I'm assuming that you already knew how to transfer from a binary number to a decimal number. If you recall, in the binary number or in any numbering system, you have the base to the power of the location. So this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on and so forth, till 2 to the power of 31. And what you need to do is just multiply 1 by the power, or whatever is there by the power, 1 multiplied by 2 to the power of 0, plus 1 multiplied by 2 to the power of 1, plus 0 multiplied by 2 to the power of 2, plus 1 multiplied by 2 to the power of 3, and so on and so forth. Then you will do all of this addition. At the very end, it will give you 11, which is basically representing that binary number in a decimal sense. Another important thing that I would like to remind you about, and I'm assuming that this has been covered earlier in an earlier course, the twos complement signed integers. And this, instead of ranging from 0 to 2 to the power of n minus 1, it goes actually from minus 2 to the power of n minus 1 to the 2 to the power of n minus 1 minus 1. So this looks the same as whatever I mentioned earlier in the previous slides. The only difference is with the last or the most significant bit. So this has the power of 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, all the way to 2 to the power of 31. The only difference that this is actually represent a sign, and I will deal with this as -1 to the power of 2 to the power of 31. When you do that, all of these things, you will find that this interesting number is not but -4. And when I have 32 bits, instead of counting from 0 all the way to the 4 gig or to the power of 32 minus 1, I am counting from this to this. And I'm assuming that you will know all of this information by heart. So basically, in these two complement sign integers, bit 31 is a sign bit. If it is 1, this is negative number. If it is 0, it's basically a non-negative number. Interestingly, that non-negative numbers have the same unsigned, basically, number as the 2's complement representation. If it is a positive number or non-negative number, basically, both of them will be the same. Let's like review some specific number. I can write 0 like that, but 2 with 2's complement, and I write -1 like that with 2's complement. Interestingly, if you write all ones, then you will get -1. You can try it by yourself, but let's take an easy example. Let's say that we have 1, 1, 1. So this is 2 to the power of 0, this is 2 to the power of 1, this is 2 to the power of 2. This will be minus, as we mentioned. So it will be -1 multiplied by 2 to the power of 2 plus 1 multiplied by 2 to the power of 1 plus 1 multiplied by 2 to the power of 0, as you can see from here. This is -4 plus 2 plus 1 is equal to -1. Yes? Although it is only 3 ones, it's still -1. All of these ones still 31 or 32 ones still give you -1 in the 2's complement domain. So if I'm asking you in a 2's complement representation, what is the most negative number? So the most negative number is not but all the numbers here that represent the positive as zeros, and this will be the only one that is high negative, yes? So it is 1 multiplied by very high negative multiplied by 2 to the power of 31 negatively without adding any positive values. So this will give you the most negative number. If I'm asking you about the most positive, it will be the other way around, that I will give ones to all the positive number and I will allocate 0 to the negative number. And in that sense, I don't have to include anything here, and this will give me the most positive number. Let's take an example with this 2's complement. If I would like, as an example, to give the 2's complements for 2. So what we need to do is not but flip and then add 1. How we can do that? This 0 will be flipped to 1. The 1 will be flipped to 0. 0 will be flipped to 1, flipped to 1, and so on and so forth. And after that, I need to add 1. 1 plus 1 is what? 1 plus 1 is 2. And how we can write 2 is 1, 0. So we'll put the 0, and then this one will be here. And then 1 plus 0 is 1. And then 1, 1, 1, and so on and so forth. And then you can write the 2's complement like that. There is also an important thing, which is a sign extension. What does that mean? Meaning if I'm writing a certain number, for instance, in 4 bits, I'm asking you, please write this number in 32 bits instead of 4 bits. How we can do that? Interestingly, the sign extension rule is saying, please do an extension by just moving or copying the signed number or the sign bit to the left. What does that mean? If this is, let's say this is a number, and I'm telling you this number, it needs to be extended, and this is signed. I know, of course, that this is the sign integer, sign bit, correct? Because always the last bit. What you need to do is just not but repeat that sign bit. If this bit was 1, please do that. Interestingly, after you look at this, it will give you the same exact value as this. This is the rule of sign extension. As you can see from here, this just took that 0, copy it several times. It just like took that number. Since the sign bit is 1, it's just like copying the ones. Interestingly, this will give you the same value as this, and you can try it yourself. This is the sign extension rule. We mentioned earlier that we have the register, and this register is 32 bits and 32 rows. We also mentioned that instead of having this as a numbers, we are just representing this by a certain particular representation. Let's say T0, T1, T8, and so on and so forth. So here I'm giving you the T0 to T7 is registers from 8 to 15, for instance. T8 and T9, 24 and 25. S0 to S7 registers from 16 and 23, and so on and so forth. There are actually a lot of other things. There will be like a sheet that will map all of these names to a certain particular location inside the register, and this will be given to you. But one of the most important things that we need actually to cover and to think about it is how I will represent my instruction to the computer. Let's say I would like to do this add S1, comma, S0, comma, S2, for instance. With your eyes, you can easily understand that I'm adding this to this, put the results in this. I may refer to this as my first source. I may refer to this as my second source. And I may refer to this as my destination. So I'm adding my first source to the second source, put the results in a destination. Okay, that's fine. This is what we can understand by decoding that from our brain, and by seeing that with easily by reading that, we can basically interpret this in that way. But the question would be how we can represent that to the machine or to the CPU or the processor. How we can represent that, because we already explained or mentioned that each of these instructions will be allocated in a 32 bits by zeros and ones. Of course, the machine, as soon as we read these zeros and ones, will understand the same thing as we mentioned here. How to represent that? How did the MIPS researchers think about something like that? We need to understand, because I might give you something general and I ask you, like, please design your format. Okay, here is my 32 bits command or instruction, and I will now distribute the bits according to a certain rules, so I can basically help or introduce to the CPU how, as a CPU, can read, how you can read my instruction. There is add or subtract or multiply. So then inside this 32, I have to indicate something or some bits to represent that this is an addition, or this is a subtraction, or this is an add immediate, or whatever the thing is, correct? The MIPS guys thought about that, and they have decided that the first 6 bits, and interestingly, the last 6 bits will be for that particular thing. They will call the first one op or opcode. The last one is a function. And by the opcode and the function, we will be able to represent whatever I have here. But then I need to mention, like, okay, I need to go to my register, go to S0, go to S0, and then add it to S2, for instance. Add it to S2, put the results in S1. So actually, I have to mention, please go to S0, and then go to S1, and then put the destination in S2, or I will go to the first source. I will call it first source here, S0, it is RS, which is here. I will call this second source, which is RT, which is here. And then I will refer to this as the destination registers, which is here. But then the second question, or the next question, is how many bits do I need to represent something like that? Interestingly, the MIPS researcher choose 5 bits for each of these. But then we need to inquire about that, or we need to ask ourselves, like, why it is 5 bits? Why they have decided that 5 bits would be enough to represent this information? Interestingly, we already knew that this register is not but 32 rows. How many bits do I need to address anything inside these 32 rows? Of course, 5, because 2 to the power of 5 is 32. So basically, 5 bits will give me 32 different locations. Do you remember the example that I gave you about the houses? And if I have 2 digits and I have a decimal, and then how many houses I can number? Yes, or I can address 0 to 99, so 100 houses, correct? This is if decimal. But if binary, if I have 5 bits, I can address 32 different houses or 32 different locations. So if I would like to let you know that please go to the 17th location plus the 18th location, put the results in the 20th location, I can do that by 5 bits. But I can't do that by 4 bits. Because if I have only 4 bits, I can address 16 different locations, not 32. In another example, I can give you like a register that is actually 64. And I'm telling you, please design your format. Of course, you won't be able to choose a 5 bits in that case, because if you have 64 different locations, 5 bits won't be enough. If you would like to go to the 63rd house or 63rd row, how you can represent this by 5 bits? You can't. If you write all ones, this is the 32nd location. That's all. What is after that? And that's why they have decided to choose 5 bits for the first source, 5 bits for the second source, 5 bits for the third source. Remember that this 5 bits is not holding the value that is inside that row. It is only holding the address of that row. So I'm not telling you what is inside the house. I'm just telling you the address of the house. And if I'm telling you the address of the house, you need to know like how many houses and how many bits do I need to address these houses. And since I have 32 different rows, so I only need 5 bits to address these rows.